Hey guys, Mr. Backberg here. In this video, we're going to look at the derivative of the arctangent. The function y equals the inverse tangent of x is defined for all real numbers, and it's also differentiable for all real numbers as well. As we're looking at finding the derivative of y equals the inverse tangent of x, the first thing I'm going to do is rewrite this using an inverse function relationship. So if we know that y equals the inverse tangent of x, then the tangent of y is equal to x. And then what I'm going to do is differentiate both sides using implicit differentiation. So if I take the derivative of the tangent of y on the left-hand side, that turns into secant squared of y, but because we're differentiating something with a y variable in there, we have to attach the derivative dy dx to that. And then on the right-hand side, when we differentiate that x, it just turns into 1. Now I want to solve to get dy dx alone, so I'm going to divide that secant squared over to the other side. So dy dx is equal to 1 over the secant squared of y. But I want to work on simplifying this down and maybe making some substitutions in here. There's a trig identity that says secant squared of some variable, so if we're using y in here, that's equal to 1 plus the tangent squared of that y variable. So we can replace that denominator, that secant squared of y, with 1 plus tangent squared of y. But then, if we look at what we said earlier, we said that the tangent of y was equal to x. So in here where we have the tangent of y being squared, I'm going to replace the tangent of y with x. So then this is going to end up saying 1 over 1 plus x squared as our derivative. Now we're not always going to be dealing with a plain inverse tangent of x. So if we had the equation y equals the inverse tangent of u, where u is some differentiable function, then as we're finding its derivative, we would have to include the chain rule. So this would be dy dx is equal to 1 over 1 plus u squared, but then we would have to attach the derivative of whatever that u function is on the inside. So in this example, we've got a particle moving along the x-axis so that its position at any time t is greater than or equal to 0 is x of t equals the inverse tangent of the square root of t. We want to figure out the velocity of the particle at a t-value of 16. So if we want to find the velocity based on the time, what we're going to have to do is differentiate this x function that we were given. So if we use that derivative that we just came up with on the last page, notice that this is a differentiable function u in here, so we're going to have to include some chain rule stuff. This is going to be 1 over 1 plus the square root of t squared. But then if we attach the chain rule derivative of this square root of t, that's going to turn into 1 over 2 root t. Now we can clean up this first piece just a little bit, because when we have the square root of t being squared, that's going to simplify down into just a regular t. So that first fraction is going to be 1 over 1 plus t. And then if we multiply by that second fraction, it's going to be 1 over 2 root t. Now we're trying to look at the velocity at a t-value of 16, so we're going to have to take that and plug that in now. So the velocity at a t-value of 16, this is going to be 1 over 1 plus 16 times 1 over 2 times the square root of 16. Now as we're looking at that first fraction, if we add those pieces together in the denominator, we're going to get 17. If we look at that second fraction, if we square root that 16, that's going to be 4, but then multiply that by 2, and that's going to be 8. So this is going to be 1/8. Multiplying those together, well, on top 1 times 1 is 1, on bottom 8 times 17 is 136. So the velocity of this particle at a t-value of 16 is 1 over 136. That's going to be it for this video. Thanks for watching.